Learn about event-driven architecture with this comprehensive course. Event-driven architecture is a software design pattern where the flow of the program is determined by events, such as user actions, sensor outputs, or messages passing between processes. Join Matt Martz and Matt Morgan as they unravel the secrets of transforming traditional apps into cutting-edge, event-driven powerhouses.
Welcome to our deep dive into event-driven architecture on AWS. In this course, we'll be going over what event-driven architecture is, along with migrating an example inventory management app to event-driven architecture. We also have a companion blog post that is linked throughout the course at martz.codes/e/deep. I'm Matt Martz. I've been an AWS community builder since the first cohort in October of 2020. The AWS Community Builder program is an incredible platform for networking with AWS professionals both inside and outside of AWS, along with a few other perks. If that sounds interesting to you, their application cycle tends to open at the beginning of the calendar year, so keep an eye out for that. I'm also a principal software architect at Definitive. At Definitive, we have an event-driven architecture-backed iOS app called Savvy Spend Smart that helps people save money. In this course, we'll dive into hands-on coding for event-driven architecture using AWS CDK. If you're new to CDK, you might find my CDK crash course with freeCodeCamp particularly useful. For deeper insights into dev tools, event-driven architecture, and serverless, you could also check out my blog at matt.martz.codes, where I share advanced knowledge and tips.
Thanks, Matt. I'm also Matt. I'm Matt Morgan. I'm also AWS Community Builder, joined at the same time as Matt Martz. I've been in the program for about 3 years. I'm currently employed as the Director of Engineering at CommentSold, which is a multi-channel live selling platform. I've done a lot of writing. I co-authored a book called The TypeScript Workshop, and I have a lot of other blog posts and things, and everything is linked, as well as some talks linked from my website, which is at mattmorgan.cloud.
Over the course of this video, we'll take a look at EDA basics such as terminology, item potency, and why you need to care about it, and synchronous and asynchronous response models. Then we'll build an EDA app using CDK, making sure to add in observability and things like that. And we'll wrap the course up by going over some advanced practices, such as considerations for how to format your events, along with some neat tools that AWS provides.
So to help demonstrate the value of event-driven architecture, we came up with a little sample application and a problem to solve in the application. So the application is a warehouse inventory management system called WIMS, because we've got a warehouse full of MacGuffins, and the MacGuffins are a very popular item, and so we need software to help us manage things like inventory management, fulfillment, payment processing, all those kinds of things. WIMS V1 is built as a microservice REST API system. So everything is a synchronous REST API call. And this is fine on a smaller scale, but as the system begins to grow up, we find that some of the Lambda functions inside the architecture are doing too many different things, and we start to see some weaknesses in the architecture. So we're going to go into this application, get a little bit deeper into it, and examine some of those problems, and then examine the solution that we solved with event-driven. So let's look ahead at what we're going to be building by the end of this course. What we want to do is we want to take our tightly coupled, entirely REST-based microservice and change it into an event-driven architecture where things are eventually consistent and have a single responsibility per component. The way this will work is that when an order is submitted via the API gateway, that's going to be persisted in a DynamoDB table. And then we'll use DynamoDB streams and event bridge pipes in order to transform that event and then emit it across event bridge, where we can create rules to capture the event and then trigger other things. So in the diagram, you can see that we're triggering a number of things off the event bridge rule. We can have our low inventory warning there. We can eventually build an external fulfillment system off of that. We have event logs, and we're going to trigger a step function that is going to handle things like adjusting inventory and processing payments. And we know that one of the weaknesses of our payment system is that we sometimes get rate limited by the payment system. So we're going to use SQS to slow down the rate of events going into the payment system so that everything can be processed in due time.
A few reminders before we get started. There's a companion blog post that reinforces what we'll be going over here. The video is split up into chapters and will have timestamped links in the description. And the sections are color-coded. The intro and outro are blue, the EDA Basics section will be green, the demo will be orange, and the advanced or best practices section will be purple. Now that that's out of the way, let's get some backend on what event-driven architecture is. Eric Johnson is a renowned principal developer advocate at AWS. He's widely recognized for his expertise and insightful talks on event-driven architecture. In his various presentations, Eric distills EDA to its core, and he simplifies it brilliantly as something happens and then you react. This succinct phrase captures the essence of event-driven architecture, but what does it mean in practice? It's helpful to think of EDA in terms of our daily experiences. As humans, we're surrounded by a continuous stream of events. These could be anything from a phone notification to a sudden change in the weather. Interestingly, we don't respond to every single event. We selectively react based on relevancy, urgency, or our current focus. And this selective reaction is a key aspect of event-driven architecture. It's about systems intelligently responding to specific events that matter. In the realm of software and cloud architecture, this translates to applications and services reacting to certain triggers or changes in the environment. Just like us, these systems are designed to respond selectively, ensuring efficiency and relevance in their operations. Eric Johnson's analogy beautifully aligns with this principle, making EDA not just a technical concept, but a relatable, natural process. So Matt, why do you think EDA is becoming so popular?
Well, I think that, in many of the tools that we like to work with increase developer productivity. When you increase developer productivity, you build more. And when you build more, you end up with more features. And when you end up with more features, then complexity really starts to creep into the system. We've all seen 1,000-line functions that try to do way too many things and are really hard to modify. So I think it's natural to say that my system's getting really big and complex, so I want to start to make it into a distributed system. I want to start to break services out. I want to start having things happen when something else happens and decouple these services in a way that makes it easier to build a wide, broad system that has lots of complexity, but that the complexity can be siloed and contained within services.
Yeah, that plus fault tolerance, and you get a highly reactive system that it's easy to extend. You can throw an intern at a problem and say, hey, add this feature to it. You don't have to worry about the intern breaking the entire monolith lambda that's handling your order system, right?
Yeah, I mean, if the intern's breaking it, it's probably my fault anyway for asking someone like that. But yeah, I mean, it's I think that isolating failure to one service as opposed to my whole system falls over is a really, really important design consideration. I also think that we find opportunities where we want systems to scale independently. One system, maybe can't take too much traffic, and another system can go very quickly. We have different levels of importance on some of the capabilities that we do. Some capabilities we might say, oh, eventual consistency is fine. Like that can happen overnight, or it can happen later. Other things we may need an immediate response. It's very hard to build systems that way when everything is sort of contained within one function. Everything just has to kind of happen synchronously, one after another. But if you can emit an event that says, something that an order has come in, or a new customer signed up, or a payment is, whatever it is, and then hook into that and say, okay, and then I want this to happen. That can be a really powerful way to build. And the other thing that I think is really important here is that a lot of us who've been in the business for a while have seen systems that sort of start with, lots of REST interactions and things like that. And then eventually we say, we can't do everything inside of one REST call. So we need something that happens, some kind of process that will happen offline or in the background. And often the solution to that has been cron. So like every 5 minutes, a process wakes up and says, do I have anything to do? And maybe it has to query a database to do that. Or maybe there's some other way that it can do that. And that kind of system can be, it's, first of all, if it wakes up and says, any work to do right now? Oh, there isn't. And then a job comes in right after that, it's going to wait until the next interval. So it's slower. Also, it's frequently waking up and saying, do I have any work to do? And finding out that the answer is no. So it's inefficient. If you can instead say, here's an event, react to the event, and then have a system that's kind of standing by ready to do that, you're going to be in a much better place. And the tools that we have now to do that, build that kind of architecture, things like Lambda, step functions, Event Bridge, those are great tools, and they do a really good job for it.
So by switching from like a cron-based server full like legacy PHP system running once a day or something like that to more of an event-driven architecture, it enables your teams to more quickly react to things and actually process data closer to on demand. That's
right. Yeah, and I think that part of this is that it's important to embrace eventual consistency and to say that things are not happening within that the 29-second API gateway timeout or whatever it is you're working with. But on the other hand, if you build event-driven architecture in a really good way, that you can often find that things are happening very quickly, and it almost seems like it's happening in real time.
Yeah, that's a good point. And I don't think we haven't gone over eventual consistency yet in this course. And maybe editor Matt should go back and add some slides on it. But what is involved in getting into that eventual consistency mindset?
I think it's just thinking about it really, because the web has already prepped us for that. In fact, even before the web was such a big part of our lives, we were it was part of our life. It was part of culture. It was something that was understood. I'm waiting for a check to clear, for example, right? I have received a payment, but that payment is eventually consistent, and the funds are not available for me to use. I mean, that's been around longer than I have. So, and I think that I think payments are a great example of that. But I also feel like if you just understand that the web is by its nature eventually consistent. Of course, you can contrive of conditions where you don't want that eventual consistency, and there are tools for that too. But by taking eventual consistency, and I know we're also talking about idempotency here, which I think kind of goes along with that, and saying that that's the default starting place. That's where I want to be when I'm designing my system, and anything that isn't living up to those principles is an exception.
Do you find it difficult to do you have to push back on maybe product people about the whole eventual consistency aspect?
I've never really had a problem with that. I think that I don't want to beat up on devs at all, really, because devs are great people. But most of the time in my career, I found that the reason that a system was built in an immediately consistent way is just because we just built it as REST, and then that became the expectation. When I go and say, hey, we're going to put a spinner on the page and then poll until this report is ready or something like that to a product person, I've never had any pushback on that. I think that as I said in the first place, it's very normal for many things in our lives to have that kind of eventual consistency. Mailing a letter, I mean, that's been around for hundreds of years, and everyone's had that expectation. And I think that that should just be part of our expectation when it comes to development too.
Great. All right, let's move on and start talking about what an actual event is and idempotency and all those things we just discussed.
All right.
Thanks, Matt. To fully grasp event-driven architecture, it's essential to understand its core components. So let's dive into 4 key terms that are fundamental to event-driven architecture. First up, an event. You can think of an event as a record of something that has already happened. It's a historical fact, immutable and unchangeable. An event is not about the current state of the system, but rather a specific occurrence or action that has taken place in the past. Next, we have a producer. A producer is the source of events. It generates and sends out events to signify that something has happened. This could be anything from a user action, like clicking a button, to a system change, like a completed transaction. Now let's talk about the consumer. A consumer is the recipient of events. It's designed to react or respond to the event it receives. This reaction could be anything from updating a database, sending a notification, or triggering a new process or workflow. Finally, we have the channel. This is the conduit through which events are transmitted from producers to consumers. The channel ensures that events reach their intended destinations, and it's the infrastructure that supports the flow and management of events, acting like a bridge between producers and consumers. Now, let's unpack the concept of idempotency in event-driven architecture. Idempotency ensures that even if the same event is processed multiple times, it won't lead to duplicate or unintended effects on the system. This characteristic is crucial for preventing creation of duplicate records or actions, which can occur in complex systems. Idempotency also enhances the overall reliability of the system by ensuring consistent outcomes regardless of the number of times an event is processed. Typically, idempotency is implemented using unique identifiers for each event, ensuring each event is recognized and processed only once in a meaningful way. A real-world analogy for idempotent systems is pressing an elevator button. Once you press an unlit elevator button, it changes its state. If you press it a second time, it doesn't unpress itself, nor can it do anything to speed the system up. So, building on our understanding of EDA terminology, let's now look at 5 key response models. These models dictate how systems communicate and handle events. First, we'll go through the synchronous model, familiar in traditional APIs where responses are immediate and direct and essential for real-time interactions. Then the async queue, where events are queued for later processing, allowing the producer to move on without waiting for the consumer's response. The broadcast model disseminates events to multiple consumers at once, ideal for widespread event notification. Next, the async bus, which acts like a central highway for events, supporting flexible multi-point communication in complex systems. And finally, we have the async router, which intelligently directs events based on specific rules inside of the producer's code, ensuring they reach the appropriate destination. The synchronous response model is more like a traditional API interaction. A sender emits a request, which is received and processed by the receiver, which then sends the response back to the sender. This model is widely used and understood in traditional application architectures, making it a familiar choice for many developers. It allows for immediate error detection, as the sender can quickly know if something goes wrong, thanks to the immediate response. The direct back and forth communication typically ensures low latency, which is crucial for real-time processing needs. But in cases of long processing times, there's a risk of timeout, which can disrupt the flow of information. As the system scales, managing and balancing the load across servers can become increasingly complex. This model often leads to tight coupling, making the system less flexible and more prone to failure if any single component fails. Ensuring that operations can be safely repeated without creating duplicates falls on the receiver, adding complexity to its design. A very common channel for synchronous response model is the API gateway with an HTTP connection. This is a pivotal component in managing synchronous interactions. API gateway seamlessly integrates with various AWS services, and it supports multiple authorization mechanisms. Because of this, even in the subsequent async response models that we'll go through, more often than not, you'll still be proxying those requests via API gateway because of the multiple authorization mechanisms and the service integrations that it provides. For synchronous responses, the channel also allows for request and response transformations. This feature is crucial for adapting and formatting the data as needed. Integration with CloudWatch also enables real-time monitoring. A critical aspect to note is that the channel requires responses within 30 seconds. This constraint is essential for maintaining system efficiency and reliability. While the synchronous model offers familiarity and immediate feedback, its limitations in scalability and flexibility and complexity are important considerations in your system design. To put this into the context of our upcoming demo app, let's talk about a real-world scenario. Imagine a customer walks into a store to check if our MacGuffin is in stock. This customer represents the sender in our model. The store worker, akin to the API gateway, is approached with the query. This worker has the responsibility to provide immediate information, just as the API gateway handles and routes the requests. So the warehouse worker checks the inventory system and provides an immediate response to the customer about the item's availability. This interaction is synchronous, mirroring the direct and immediately response expected in the synchronous model. However, if the warehouse is huge or the worker is busy, it may take time to get the response, highlighting the synchronous model's potential for timeouts in real-world scenarios. Next, let's discuss the async queue response model. Here, a producer sends messages to a queue and receives an acknowledgement in return. Separately, a consumer polls this queue to retrieve messages, also acknowledging once the messages are processed. This model allows the receiver to control the rate at which it processes messages, preventing overload. It accommodates processes requiring longer compute times as messages can wait in the queue. In the case of failures, the model also facilitates recovery as messages remain in the queue until successfully processed. Services like Amazon SQS can offer idempotency, preventing duplicate processing of messages too. But the model only provides acknowledgement of responses, which can limit the information available about message processing. And while it enables recovery, the time to recover can be significant depending on the queue size and processing speed. Typically, a single consumer processes the queue, which can be a bottleneck in high volume scenarios. This could be a single Lambda function spread across multiple parallel invocations, but you would not have different Lambda functions reading from a queue. Despite being asynchronous, there's still a degree of tight coupling as the consumer is directly dependent on the queue's structure and format. It has to be created and exist. In the context of async queues, our main channel is SQS, or Simple Queue Service. Simple Queue Service plays a crucial role in scaling and fortifying the architecture, efficiently managing message queue and ensuring smooth processing. However, with standard queues, be mindful of potential duplication and ordering issues, where messages might not always be processed in the order they were sent. SQS uses a polling model, which can introduce latency, as consumers periodically check for messages instead of receiving them in real time. Also, there's a size limitation to consider. Each message in SQS can be up to 256 kilobytes. Monitoring SQS is reliant on CloudWatch, which provides insights into the queue's performance and message flow. Now, talking about a real-world analogy, let's imagine our fictional app's warehouse has to send out a MacGuffin. The warehouse producer sends the MacGuffin, the message, to the shipping company, the queue. From there, the shipping company manages the storage and eventual delivery to the destination. It receives one MacGuffin and delivers one MacGuffin. It doesn't copy the MacGuffin, it's one-to-one. Next, we'll explore the broadcast response model, also known as publish-subscribe, PubSub. The arc diagram here illustrates a producer sending a message to a topic and receiving an acknowledgement in return. This message is then distributed from the topic to two separate consumers, showcasing the multi-receiver capability of this model. In this case, one message is copied and sent to each consumer. An advantage of this model is its ability to handle processes that require extended computation without burdening the producer. The model excels in scenarios where one event needs to reach multiple consumers, as demonstrated in the diagram. It supports a variety of communication protocols, offering adaptability to diverse system requirements. A challenge in this model, though, is the potential for receiver failure. If a consumer fails, it might miss out on important broadcasted events. Despite its broadcast nature, there's a level of tight coupling as consumers need to subscribe to specific topics to receive messages. Ensuring that events are processed uniquely and not duplicated falls on the consumer, adding an extra layer of complexity. In the broadcast response model, our main channel is SNS, or Simple Notification Service. SNS excels in one-to-many messaging, enabling a single message to reach a wide array of recipients simultaneously. It operates on real-time, push-based notifications, ensuring immediate dissemination of information. SNS uses a topic-based pub-sub model, where messages are published to topics and then pushed to subscribers. The service supports a variety of subscribers and communication protocols, catering to different system needs. However, it's important to note that SNS does not inherently provide message ordering or duplication handling, which might require additional handling in the consumer's logic. For a real-world analogy, consider our MacGuffin warehouse inventory management. Suppose the warehouse must quickly update various departments, sales, shipping, customer service, about changes in the MacGuffin stock levels. When a new match of MacGuffin arrives or stock levels change, a single announcement is broadcasted to all relevant departments. For event bus routing, our architecture diagram has a producer that emits two types of messages: new user and updated user. These messages are sent to the event bridge bus, where rules on each of the types forward them to their type-specific consumers. There could potentially be a third rule that forwards both event types to another lambda. Similar to SNS, this is a many-to-many situation where many types of events can go on the bus, and each of those events can be directed to multiple consumers. A key advantage of this model is its loose coupling. Producers and consumers operate independently, enhancing system flexibility and maintainability. It's well suited for processes requiring extended computation, as message processing is not tied to the producer's timeline. Like other async response models, one limitation is that the response model primarily provides acknowledgement responses, which might not offer detailed feedback on message processing. Recovery from failures or message losses is managed by the consumer, adding complexity to its design. And ensuring item potency or preventing duplicate processing is also up to the receiver, which can be challenging in complex event scenarios. For the async bus response model, our primary channel is Amazon EventBridge. EventBridge excels in handling complex event routing, directing specific events to the right destinations based on detailed criteria. It offers seamless integration with a wide range of AWS services, enhancing the model's connectivity and utility. Users can create custom event buses tailored to their specific application events, offering greater control and customization. The schema registry feature aids in managing event models, ensuring consistency and clarity in event handling. One notable limitation is the lack of direct support for message queuing within EventBridge, which may require additional considerations for message handling. A real-world analogy for the async bus is very similar to the broadcast scenario for stock levels. EventBridge routes specific events based on defined criteria. When stock levels change, an event could trigger updates to the inventory team, sales department, but not the shipping dock because it didn't hit the threshold in their rule. Each department is a consumer that receives events based on their own set of rules, so it's a much more flexible system than SNS. Finally, we have the async router, a multi-model event routing approach. The architecture diagram here illustrates a producer that's not just emitting events, but also handling the routing logic. It routes events to the various response models we've been discussing based on its own internal business logic. A significant advantage of this model is the greater control it provides over the event routing. The producer directly manages where and how events are routed, allowing for specific event handling. Having said that, its advantage is also a significant disadvantage due to the extra complexity that you have to add to the producer's codebase. The model also introduces tight coupling, as the producer is intricately linked with the routing logic. This type of system could be exceptionally difficult to maintain. So Matt, after having gone through the 5 different response models, we've already discussed going from kind of the synchronous mindset. We've talked about the flexibility moving to event-driven architecture. Should teams just use EventBridge by default for everything as their starting point in EDA, or what do you think?
Well, I think EventBridge is a fantastic service, and I'm a huge fan of its many capabilities. I was a little bit late to the pipes game, actually, and I'm just really impressed with what you can do with pipes, and I can't wait to see what else you can do with that in the future. That said, there are a number of other tools that I think are really useful here too. And so to say, let's throw everything over EventBridge, I think sometimes so definitely do use EventBridge. People should use EventBridge when building event-driven architecture. It's right there in the name, but more than that, it's a really great service. I think that there needs to be room here for step functions as well. Step functions can be a target for an EventBridge pipe or just a rule. But sometimes you've got things that you want to happen in a certain sequence. And if you're just firing events off, you're just saying, here's an event, and then I've got 7 different listeners, and all those listeners are going to do their own work, right? But maybe I want to know, when are all those listeners done, right? Well, they can all fire events too, but it doesn't kind of come back together and say, okay, everyone's done. Here is the top level completionist of it. I would have to build something to do that, right? I would have to track all of those events coming back in the end, and then saying, okay, now I'm finally done. I finally reached the end of this. It's much easier to do something like that with step functions. So you can fire the event, you can have a step function that says, okay, I'm going to do all these different things, but I'm going to do it within a container, and then I'm going to understand that job has finished. And then I can have my reporting, I can have my final status, whatever needs to be done at the end of that. So I think those two things, they work really great together. So I always think about EventBridge as being like, if system A needs to talk to system B, or something like that, or system A just needs to say, hey, something happened, who cares? And then you can have rules that pick that up and do things with that. But if you've got, I need these 7 things to happen, and I need them to happen in a certain sequence, I wouldn't just build that over EventBridge. I would definitely leverage step functions for that.
Yeah, that's a good point. And that reminds me of like a blog series or a blog post by Yan Sui, the Burning Monk, about orchestration versus choreography, which basically covered the whole, like, should you use EventBridge or should you use step functions depending on the task.
That's a great look at the question.
I think you can mix and match the two, and I've written about this too, and I think Jan has also. But like you can combine the two by adding put event notifications as part of your step functions flow too, so you understand as certain sections of the step function completes, you can maybe trigger things.
Yeah, I don't think we're getting into that in this course. Maybe a future one, but using pass tokens and step functions and sending those out over Event Bridge, and then eventually getting a response back to restart your state machine. It's a great pattern. I love using that.
Yeah, awesome. Okay, so our next section, we're going to switch over to demo mode. So we're going to go over migrating our legacy app into CDK, or well, not into CDK, into event-driven architecture.
All right, let's do it.
So now that we know a bit more about event-driven architecture basics, let's get into the actual demonstration. To do that, we're going to be using AWS CDK. AWS CDK is a cloud development kit. It's an open source software. It's where you can write imperative code to generate declarative CloudFormation templates. Now, we just learned about the concept of idempotency, and CDK is idempotent. The same inputs that you give to a CDK stack will yield the same exact CloudFormation YAML. If you somehow get into a scenario where it's not, and it's not deterministic, then you're doing something wrong with CDK, so you should take a look at that. If you haven't been exposed to CDK before, I've made the CDK crash course for freeCodeCamp before, and that's linked at martz.codes/v/CDK.
All right, so let's get back to our WIM system and look at the version 1 of that system and the kinds of problems that we had with it. So it is an API gateway Lambda DynamoDB system. We got a couple of Lambda functions here, just two for demo purposes, but in the real world example, we probably have more. And we got the check inventory function, which is pretty straightforward. That one's probably fine, but our create order Lambda function, it has a few problems. The problems really is that it's trying to do too much. It's trying to do too much, and it's got, of course, Lambda has a 15-minute timeout. Nobody wants to wait 15 minutes, but we can anyway because API Gateway has a 29-second timeout. So that means that it has to do all of its work within that window, or the user is going to get a 504 error back. So it has a couple of things that it's doing in a DynamoDB table. It's saving an order and it's updating the inventory, and those ones are probably okay. We'll come back to that in a second. Like you can probably do two updates to calls to DynamoDB inside the Lambda function. But the process payment one is one that we're really concerned about. So let's say our system, it does this thing. It is, we are calling our payment microservice, which is a separate service that, maybe another team maintains. And we understand that that's an eventually consistent thing. It's not going to do all the payment processing within the request that the Lambda function is making to it. But it is, let's say it's not a perfect microservice. It's a little bit slow sometimes, and sometimes we get rate limited. Sometimes it just can't handle the amount of traffic that we send to it. So this is a really big problem now, because our Lambda function is going to try to call the payment processing system, and sometimes it'll get rate limited. So what can we do? We can do some retries within the Lambda function. We have a very limited time window for those retries, and if we can't complete the retries within the 30 seconds, then what's going to happen is that our user is going to get an error, and they're not going to know that this was successful. Okay, so that's a big problem. We have to fix that problem. There's a lot of different ways to fix that problem, but it is a big problem. The other problem that we're facing here is that we're saving the order, we're updating the inventory, and then we get a requirement that we didn't restock our inventory in time because we didn't know how low it had gotten, because we had just a doorbuster of a day of selling MacGuffins. So what can we do? We need some kind of notification system that lets us know when our inventory gets low. Well, one way we could do that is we could say, after we do the adjustment, we could check the current level against whatever our watermark is for low inventory. And if we're below that, we could post a message to SNS that's going to send us an email to let us know that our inventory is low. That's it could work, but our Lambda function was doing 3 things. Now it's going to be doing 5 things, which just means that there's more things that could go wrong. But the other problem that is, what if our inventory gets adjusted by something else? Maybe there's like an admin override or something like that, or maybe there's other sales channels or something like that. And if the logic to send that notification that we're low on inventory is only in this function, then any of those other channels that take our inventory to that low level are not going to send the notification. So basically, that's just really not a good solution. And then finally, if you see the bottom of the diagram here, we're thinking about building this fulfillment system. But how do we know when there's a new order based on this system? We're going to send another request out, to notify that. We're going to have a 6th thing that this Lambda function does. We're kind of collapsing under the weight of all the different things that we're expecting to do here. And we really need to start sending us some events, because having an event that says, hey, there's a new order, do you want to do something with that, is going to be a much more robust architecture. All right, so let's look at the event-driven version of this. So we made a few changes here. First of all, and we'll see this when we look at the code, we've gotten rid of some Lambda functions. We brought in another Lambda function because we kind of needed to. We switched to some direct integrations between API Gateway and DynamoDB, and that's really because putting a DynamoDB put statement or a get item statement or something like that in an API Gateway template is really pretty easy, and it's not very much different from putting it in Lambda. You avoid the cold starts, and we're basically stripping down our system to make it much simpler. Some people may not be comfortable with that. You can still use Lambda. It's not like a bad solution or something like that. But here we're just trying to strip it down to the bare minimum. Now, what we're doing is that when we create an order, the first thing that we do is we're going to persist that in the database. This is a little bit flipped around from the way many systems work, which is that, okay, an order comes in, we have a bunch of business logic that we need to execute against, and then we finally save it in a table somewhere. Here, what we're going to do is we're going to say, okay, order comes in, we immediately save it. So we're basically capturing the user's intent in what needs to happen later on, and then we're going to emit events based on that, right? We don't have any additional logic at that stage. We're just say, store it, send the event. Okay, so DynamoDB streams are a great solution to this, and a lot of this architecture is based off that. If you happen to be using DynamoDB, it's a good way to go. If you're not using DynamoDB, you can emit events in many other ways. This is just a great way to get started. So those who've used DynamoDB streams before know that it's recommended that you only have 2 consumers of a stream. And that has to do with polling and some internal concerns there. A good solution to, or I guess a good pairing with DynamoDB streams is to use event bridge pipes, because you can subscribe the pipe to the stream, and then from there you can enrich the data that's coming through. You can transform it in different ways. You can do that with a Lambda function or a step function. You can do that with just a very simple mapping template if your need isn't that complex. And then that can be reposted to Event Bridge, and now you can create rules to send it different places. So in our architecture, we have the stream coming through. We're going to enrich the data in that stream. So basically what we're going to do is we're going to unmarshal the DynamoDB syntax to make it a little bit easier to work with later in the process. And then we're going to repost that event back to Event Bridge. From there, we can create a rule that is going to give us that low inventory notification. We'll show how that works a little bit later. It's very cool, I think. We're going to store event logs. This is kind of a new thing. It wasn't in the old system, but anytime we have a change, we're just going to throw that into CloudWatch so that we can see what are all the different change events that are coming through. And of course, very importantly here, we still need to adjust inventory and we still need to process the payment. We're going to use a step function for that because we want both of those things to happen, and they're kind of related and pertinent to the order. So the step function is going to directly, again, with just a direct integration, it's going to make the inventory adjustment into DynamoDB. You can do that with a condition statement to make sure we don't end up with negative inventory or something like that. And notice that feeds back in. We get another change event, which is going to then encounter that rule that will notify us if our inventory got too low. The last piece of this is that we have put an SQS queue in between our order process and the payment processing, so that if we get rate limited, the message should stay on the queue and then gets consumed a little bit later. That's done by means of another event bridge pipe. One thing I'll mention is that particular piece of this architecture of saying my downstream service might be rate limiting me, so let me put SQS and event bridge pipes in between that. It's not something I've done production before. We might find that doesn't work as well as we thought it might. We might need a more robust solution. That could be swapped for a step function later on, and the rest of the architecture doesn't have to change. So that's a really great thing about event-driven architecture, is that you can replace components that aren't quite living up to what you expected them to do, and the rest of the architecture doesn't have to change. On this diagram, just wanted to show that the motion here, where we had a Lambda function that was doing check inventory in the V1 architecture. In V2, we're doing that as a direct integration. It's almost the same thing. But that save order, it was doing multiple things before. Now we have single responsibility components. So we have a direct integration that persists the order in our table. And then we've got the Dynamo stream that eventually, but very quickly actually, will trigger that step function that is going to do the inventory adjustment. That we've got some new features here. We got our low inventory notification that's very easy to implement, and we can build that external fulfillment system based on the event. We've got event logs, and we've got that queue for our payment processing. And while we're at it, we could think about additional events that we could add to this system. What if we wanted a high inventory warning that says that we've overstocked and our sales team needs to get active? What if we want an out of stock notification that then can flag that in our catalog as on back order? There's lots of different things that we could conceive of, and they're all going to be fairly easy to implement and fit this model. All right, everybody, let's look at some code. So what I have here is the WIMS v1 system. That's the REST API-based system. And this is the CDK code. So I'm just going to walk through this really quickly. There's not a lot here. And you'll be able to view the GitHub later on. I suggest you check that out. It's a little bit different by then, but it's going to be mostly the same thing. So we've got a table construct. We're going to create our DynamoDB table. That's pretty straightforward. I've whinged and moaned a little bit about the payments API. For demo purposes, what I did is I just created a mock integration in a separate REST API that always returns a 200. Actually, that seems like a pretty nice service, but it doesn't actually do a lot. I added some throttling to that just for fun, so we can benchmark that. Then I created a couple Lambda functions. There's the one to get inventory and the one to create orders. We'll look at the source for those. Get inventory is super simple. So I'm using the DynamoDB document client, and I'm just going and getting a specific item. So there's one item in the table for each inventory. Now, probably I would do something a little, we'd probably have more than one thing that we can sell. And there'd probably be some kind of query param or something like that that includes the skew or something, and we use that to actually generate a query. But in this case, just to keep it really simple, there's exactly one thing, and so we're just going to go get that, and it's going to tell us what that inventory number is. All right. Create order is a little bit more complex. We've still got DynamoDB document client here. And first of all, we're going to toss that guy in our table. We're going to generate a partition key and sort key for that. We're also going to set the status of it to pending. You won't actually see that status change in this demo, but you can imagine that some other system later on would update that. Then we also have to have an update command that's going to go and reduce the inventory for that. And finally, we're going to make a fetch call using native node fetch to post our order over to the payment system and get that payment process started. Then we return order created, and everybody's happy, right? The only other things that you would see in this stack are just a couple of really quick things. We've got our REST API for the orders API. We've got a couple of resources there to connect to the Lambda integration. And then finally, there's this AWS custom resource, which is just to seed the database so that when I deploy my stack, I'm going to have it preceded with that LX model MacGuffin with a quantity of 1 million items. All right, so let's walk through the modern architecture. It's going to be pretty different here. First of all, what I did is the V1 version of WIMS had everything just inside of that WIMS stack class. Our V2 version has a few more things going on. And so what I did is I built some L3 constructs. L3 constructs combine various things, other resources that I want to create, and kind of put them behind my own vision of what the application actually looks like. So so those are just really, in this case, I'm not anticipating any reuse. It's just sort of an organizational construct. So I still left the table here. I could have created an L3 construct just for the table, but it would really be exactly the same as this L2 construct. So it's just fine to do that. The only thing I might save a few lines here of config. Hardly worth it, as you can see that I've only got a little over 40 lines of total code here. So let's look at some of these individual sections of it. The first is CDC, which is, of course, stands for Change Data Capture. And we've got several things happening here. I'm declaring a Node.js function, which is called CDC enrichment. Let's just check that one out really quickly. And basically what this is doing is we're borrowing the unmarshal utility from util DynamoDB, and we're using that to transform our DynamoDB record into something that's a little bit easy, into pure JSON, because DynamoDB always specifies the type in a way that is a little obtuse to work with later on. So that's really all this is doing. We could do other things here if we wanted to. This is just code, and we can do anything that we want. We are adding a meta tag that lets us know what process this. We're adding this data key, and so then we're kind of putting this in a format that's going to make sense to us, and a schema that will be happening later on. So that's the function that is going to be enriching what happens in the pipe. Let's look at what the pipe is here. So
Matt, for the enrichment function, what's the output of that going to? Like so it's outputting a list, right? It's processing a bunch of records. What does that list end up becoming?
So the output of the enrichment function is sent to the target of the pipe.
And for this specific pipe, the target's event bridge, right? So the response list is going to end up being the details of all of the events that will be going out.
That's right. That's a really good point to make. All right, so let's go back and look at our pipe construct. At the time that we're making this recording, there is not an L2 pipe construct, so we are forced to fall back to CFN. We're not actually forced, because there is an RFC for an L2 pipe construct, it's still in RFC status. You can use it. I have used it. It's kind of good. I went with CFN pipe just because it's not actually part of the CDK just yet. And CFN pipe is okay to use. You have to do a little bit more manual stuff. For example, I have to create a role explicitly because CFN pipe is going to want the ARN of that role. It's just a thing that it does. I added a bunch of log configuration here. It's a little bit optional, but it's really good, especially when it comes to debugging, as I had to do that. You can see that there's an enrichment key here, which that's going to expect the function ARN. The L2 construct would just take a function as an argument in this case, because this is corresponds directly to CloudFormation. It's going to want the ARN. We set the source here. So the source is going to be that table stream. This subscribes the pipe to the DynamoDB stream, which is configured here in our table v2 construct. We're setting some parameters here, a batch size of 10, which means that we'll not process more than 10 items at a time, and our starting position will be the most recent change. We are targeting this back to the same event bus, which is going to be our default bus, as discussed previously. And we're adding some additional parameters that this will help us to route the event when we create a rule for this. Our change data capture, all it's doing is it's saying there's a stream of data coming in. It could be a creation event. It could be an update. It could be a deletion. And we're going to use our Lambda function to enrich that, just because the transform capabilities and event bridge pipes isn't really up to what we want it to do for this, for our purposes here. And then we're going to send that back to event bridge. If we never created a rule for it, it would just kind of never go anywhere from here. But our other components can start to build those rules. So let's look at those. Here we have our order processor construct. We're going to grab that default event bus, and we're declaring a state machine. There's a few different ways to do this in CDK. I like to use the constructs. So we've got a parallel construct here. There's not much to say about it. And then we've got an update, Dynamo update item construct here. Now, this is really not very different from using the SDK and TypeScript, so I'm pretty comfortable doing it. This could be a Lambda function that does this instead. In this case, this was actually missing from the V1 architecture, so that's another little improvement that you get here. There's a condition expression here that makes sure that we're not committing more quantity than we actually have. So this would fail if we had 99 in stock and tried to sell 100. Assuming that condition is successful, then we are going to reduce the quantity. Our other branch here is basically we're just going to take that message body that came in, and we're going to replay that on SQS. We're going to stick that in the queue. Whoever subscribes to that queue, we don't know at this point. We're just sending it off. And then how does this thing get triggered in the first place? Well, here's the rule that does that. Now we've got that source and event type that we set in our CDC construct. And here we are going to create this rule, make sure that we're only getting insert event types, and that our partition key begins with customer. We could further refine that if we wanted to, and then we're going to target our state machine. So the event now becomes the input to the state machine. Let's look at our payments API. So I moved that mocked integration API here, as well as the throttle plan. This is really unchanged. Just wanted to make sure that it had its own construct. The payments processor is the piece that's a little bit more interesting here, because we've got another CFN pipe with its own role and its own logging solution. This is the queue that is going to consume messages. The messages go into the pipe, but this pipe, instead of replaying an event over Event Bridge, which actually, come to think of it, is probably the way I would like for our payment system to work, but somebody else is working on that, or nobody's working on that. So its payment system isn't going to change much in this cut. So what we're going to do is we're going to target that API gateway with this. So we can actually have our pipe connect SQS as messages come off the queue, and we pull them in. We're going to replay that to API gateway, and that way we can manage our rate limit. A couple more constructs here to go through. Our inventory monitor. This one is really nice. So all we have to do is we're grabbing our bus again. It's just the default bus that already exists in the account. We are creating an S topic with an email subscription so that our team can be notified when this event goes out. And then we're going to create another rule here, but this rule has a numeric comparator. So we say if our inventory is less than or equal to 100 items, 100 units, then we're going to trigger this rule. Finally, we've got this observability construct, and this creates another event bridge rule that is going to store all of our events in a CloudWatch log group, and it's going to create an event bridge archive and schema registry for all the events that we're sending. Okay, so I just want to, I've got the view here of my DynamoDB table in my account where I've deployed the WIM system. And I just want to kind of give a really quick demo here of how it can work. So you can see that I have preceded my database. I've got my LX MacGuffin ready to roll, and I've got 1,000 items in stock. Over here is over here in Postman, I'm going to create a post to the orders API in order to create a new order. So I've got set my customer ID to 123, and the quantity is 3, and presumably there'd be some more interesting information here. So if I send that over, and then I flip back to my table, you can see that I have registered my order, and my quantity has already been decremented. So it was that quickly. It was even faster than that my state machine ran, and all the other pieces happened. And so it almost seems like it's probably even as fast as it was before. So what happened behind the scenes? Well, one of the things we know, it was that my step function ran. And so this is the step function. You can see that it's got two branches in the parallel step here. One of them is adjust inventory, and the other one's in queue payment. They were both successful. What I think is really cool about this is look at how fast this thing was. It was 136 milliseconds from start to end, and this thing just really blazed. It got the work done very, very quickly, and because this is an express step function, that means that it's going to be very, very cheap. In fact, really, unless I'm doing this quite a lot, which would be a good problem to have, let's face it, because that means I'm selling quite a lot. It's the cost of running this is going to be negligible. In X-Ray, we have a little bit of a problem here, which I hope is a problem that service teams ultimately solve for us, and that is that you actually don't get to trace over a DynamoDB stream. So in this case, you can do traces over Event Bridge, but the stream kind of ends the trace. So we see the initial trace here, which is that our client has placed an order, and that's going to hit the DynamoDB. We'd really love to see a line that comes from DynamoDB over to the, which really the stream and the pipe here is the client, or triggering the state machine. And we can see that we're doing another operation on our WIMS table, and we're putting something in SQS. But there's obviously some missing pieces here. So that means that really in the end here, we're going to have to kind of put together some kind of additional observability elements that will let us know, hey, we had X orders come in, and Y ended up in this status, and Z ended up in this status, because we don't get the full trace here. We do get good traces for, if we want to dive down and look at, okay, just that initial save or something like that. Like if we start seeing errors, something in this area, this is a great tool for that, but unfortunately it doesn't yet give us the whole end-to-end view.
So Matt, if I was a team implementing this, what approach should we take to iteratively do it? Should we maybe start with the observability construct and the change data capture, or is there a better approach?
Those are both, the great thing about those constructs is that they're completely non-destructive, right? They're just adding additional information. The observability construct is going to start registering events and give you some additional logging, and the CDC, right? Until you subscribe to that event and do something meaningful with it, you could implement that and then just see what it does and see how you like it and see whether it makes sense to you.
So you can have the change data capture stuff independently of everything. Get those events flowing, and then even skip the stuff and like automate the fulfillment part, or automate the low inventory notification part without even touching the existing V1 code, and then
absolutely.
Or you can just spread it out and have multiple teams, one adding the fulfillment, one adding the inventory, and in turn, adding the step function or whatever.
That's correct.
I guess calling out one more thing, the distributed nature, or the decoupled nature of this, if ultimately business comes back and doesn't want to know about low inventory notifications, for example, you can just delete that construct and you don't have to go in and modify the original Lambda, the order processing Lambda like that. It's
right. I mean, I think that's, to think of your overall application platform as a series of components, all of which are replaceable, is a great architectural mindset to have, because it just makes pivots, it makes new requirements, it makes, maybe the state of play has changed in some way, and you have to respond to new business pressures. And if your architecture is modular enough, then that's going to be a lot easier to do than if you've just got sort of like this sprawling classes and functions that are much harder to iterate on.
Now, let's move on to advanced practices for event-driven architecture. Proper event formatting is crucial for maintaining system integrity, scalability, and interoperability. Enforce strict backward compatibility in your event structures. This approach reduces the risk of breaking changes and ensures smoother evolution of your systems. Keep your event properties consistent across all events. Consistency aids in predictability and eases integration across different parts of the system. Avoid optional properties in your event schemas. Ensuring that all properties are mandatory simplifies processing logic and reduces ambiguity. Ensure that event sources are consistent within a single code repository. This consistency is key to traceability and manageability of events. Different code repositories should not emit the same event source. Unique sources prevents conflicts and improves clarity in event handling. Build a standard metadata object for all events. This metadata should include essential information like the event type, the timestamp and source, providing a uniform context for each event. Place your actual event payload under a dedicated data object. This separation ensures that the payload is clearly distinguishable from the metadata. Let's talk about what should be in the metadata of an event's detail. Include idempotency IDs in the metadata. These unique identifiers ensure that each event is processed only once, preventing duplicate processing and enhancing reliability. It's essential to track where events originate. You can use identifiers like the default Lambda environment variables, the AWS Lambda function name, or things like the step function execution ID, and store those in the metadata object. This tracking provides clarity on the event's journey and aids in debugging and monitoring. For more insights into effective event payload patterns, you could check out David Boyne's blog post, which offers valuable perspectives. I also wrote a blog post not long ago delving into inferring architecture by using the metadata from event details. As an example of a well-structured detail object, the meta object here includes incoming details like the account, source, and detail type, as well as the function name and state, machine, or job identifiers. This structure aids in tracking the event source and path. Under the data object, we would place the actual payload of the event, and this clear separation between the metadata and the payload simplifies processing and interpretation. When producing events, there are two primary types, full and sparse. Understanding the differences in applications of each is key to efficient event management. Sparse events carry minimal information about what occurred. They're lightweight and typically include just enough data to identify the event and its basic context. The advantage of sparse events is their simplicity and reduced load on the system, making them efficient for high volume or real-time scenarios. In contrast, full events are more detailed, including extra information that might minimize the need for subsequent queries. While they can be more convenient by providing comprehensive data up front, they can also increase the computation burden on the producer and can be heavier on the network. There's a spectrum between full and sparse events. The choice of which to use depends on the specific requirements of your system, such as response time, network bandwidth, and data processing needs. Remember, with extra information comes more risk. More data can lead to increased complexity, potential privacy concerns, and a higher chance of data becoming stale or irrelevant. Regardless of the type chosen, it's crucial to avoid breaking changes in your event schema. Ensure backward compatibility to maintain system stability and reliability. When designing events in event-driven architecture, it's crucial to consider the nature and handling of the data within your payloads. As a general rule, avoid including sensitive information in event payloads. Exposing such data can pose security risks and compliance issues. If sensitive data must be included, consider encrypting it at the field level. This approach helps preserve the ability to perform pattern matching while safeguarding the sensitive data. Be mindful of payload limits. For instance, Amazon EventBridge has a payload limit of 256 kilobytes. If your event data exceeds this limit, an alternative strategy is to upload the larger data to S3 and then emit an event containing the bucket and key combination. This method not only circumvents the payload limit, but also leverages the robust storage capabilities of S3. Remember, if you're using S3 buckets, consumers of your events will need independent access permissions to read from these buckets. Ensuring appropriate access controls and permissions is critical to maintain security and functionality. Change data capture events are a pivotal aspect of event-driven architecture, particularly when dealing with database changes. These events are produced in response to modifications in a database, providing a real-time data stream reflecting these changes. Key to change data capture is creating a consistent event interface. These interfaces typically include information like the columns that were changed and stringified representations of data values before and after the change, the diffs. Such structured information helps in understanding the nature and impact of changes made to the database. I've written some blog posts that can help with this, On Aurora, if you have an Aurora MySQL database, you could use binlog streaming as a source for your change data capture events. Or for MySQL or Postgres, you could also use the database migration service and pipe the events to Kinesis, and from there go to EventBridge or wherever. Fortunately, DynamoDB is much simpler, and you can just leverage DynamoDB streams to create events. These can be efficiently integrated with EventBridge pipes for seamless event handling. To the right is an example of a change data capture structure. In my example, I made the detail type CDC update, and in the details data portion, I included the information about the source of the change, the database and table, along with a list of columns changed, and before and after attributes with stringified JSON. We use stringified JSON for the before and after fields to keep the interface consistent. If the event bus has schema registry enabled, and the before and after fields were not strings, a new version in the schema registry would get created for every combination of field change. But with the stringified format, we have the information we need between the combination of columns changed and before and after, and we maintain a common interface. I'll note that a CDC insert event would not have the before attribute, and a CDC delete event would not have an after attribute. They aren't optional in these cases because they are different detail types. They're different interfaces.
Hey, Editor Matt here. I just want to point out that stringified before and after bodies aren't necessarily for everyone. It's a consideration if you want to maintain consistent interfaces, but what it does do is it breaks event pattern matching inside of the deltas. So, for example, in our demo app, we actually didn't stringify the data, and we used the change values inside of the change data capture event to do the low inventory notification. So that's an important consideration for how you want to manage your change data capture events and whether or not you care about the schema registry incrementing the version every time. At the end of the day, it's probably not a big deal. I did want to point it out.
Event pattern filtering plays a critical role in efficiently routing and handling events. EventBridge offers highly flexible event pattern rules. These can include various patterns such as using a prefix, suffix, wildcard, anything but, and numeric, and others. Such versatility allows for precise event matching according to specific criteria. Best practices indicate that you should be cautious to avoid writing patterns that could create infinite loops, an event triggering another event in a cyclical manner. That could lead to system overload and unpredictable changes. You also want to make sure your event patterns are as precise as possible. Vague patterns may lead to unintentional matching, causing noise and inefficiencies in event processing. Always specify the event source and detail type in your filters. This practice narrows down the event scope, ensuring only relevant events are processed. Include the account and region as filters for enhanced security too. Utilize content filters to further refine event selection, focusing on specific event attributes or values within the event payload. A schema registry can play an important role in managing and maintaining the structure of event data in event-driven architectures. It ensures a consistency, clarity, and compatibility across different parts of the system. Start by defining clear and concise schemas at the beginning of your project. Early definition helps in establishing a strong foundation for your event data structures. And implement version control for your schemas. As your system evolves, version control ensures that changes are tracked and managed systematically. Regularly enforce schema validation. This practice helps in catching inconsistencies and errors early, maintaining the integrity of your data. Keep a detailed record of any changes made to your schemas. Proper documentation is crucial for understanding the evolution of your event structures and for troubleshooting. Implement notifications for schema changes. This keeps all the stakeholders informed about modifications, ensuring that everyone is aligned with the latest schema updates. And finally, consider using tools like Event Catalog by David Boyne for managing your event schemas. The Async API initiative is another valuable resource. It provides tools and standards for managing asynchronous APIs. Many AWS services emit events to your account's default event bus and event bridge. These events can range from changes in service states to specific actions executed within the services. You can create powerful automation within your AWS accounts by tapping into these default events. This enables real-time, responsive actions based on service activities. To effectively document and manage these, previously I wrote a 3-part blog series on event-driven documentation where I tied into these AWS service events to automatically update my org's documentation anytime a CloudFormation stack deployed with event bridge rules or API gateways. In Event Bridge, there are 2 types of buses: the default bus that is included in every AWS account, and custom named buses. Understanding their difference is key to effective event management. The default bus is always available, ensuring a foundation for loose coupling and better collaboration. It receives AWS service events automatically, making it ideal for integrations across multiple services and teams. Custom named buses offer more control, tailored to specific requirements. While they provide tighter access control, they are more challenging to share, making them better suited for single teams or projects with specific access needs. While custom named buses have their place, I recommend prioritizing the use of the default bus wherever possible for its ease of collaboration and broad integration capabilities. EventBridge Pipes is a feature in AWS that simplifies point-to-point integrations between event sources and targets. It is designed to reduce the complexity and coding requirements in developing event-driven architectures. You can create a pipe to receive events from supported sources and optionally add filters for specific event processing. Further, you can define enrichments to enhance event data before sending it to your chosen target. Pipes support various integrations, including Lambda functions, step functions, and API calls, allowing for versatile and dynamic event handling. For example, a pipe can link an Amazon SQS message queue to an AWS step function state machine with an EventBridge API destination for data enrichment. This setup exemplifies efficient automation in an e-commerce context.
So Matt, now that we've come to the end and learned so much about event-driven architecture, what's next? How do people get started doing this?
So I think kind of as we talked about it in the demo a little bit, like an easy way is to just start producing events, even if you don't have consumers to use them. You can do that by adding in change data capture, depending on what system your database is on. Or you could, if you have a server full or a serverless system, both could just start putting events on the event bus, right? And I think it segues really easily to once you get towards like decoupling your system by emitting events, like you can really segue into domain-driven development and really break things up into like teams. There's a concept called event storming also that you could kind of approach with your team to see how you can break things up into domain-driven development. Have you used event storming or domain-driven development in your workplaces?
Sure. Yeah. I mean, I think we definitely need to think about the business domains that drive our applications in order to make sure that we're working on the most important things. So considering the business domains that we have to work with, like oftentimes that becomes a discussion around microservices or bounded context. But I think that thinking that in terms of events, because whether or not we're using EventBridge, whether or not we're using event-driven architecture, of course we have lots of events, right? Like click streams, different things that happen in the system. Identifying and naming business events that we care about as things that become features of the system, as opposed to sort of like a side effect of some code, I think is a really strong pattern to start to make sense of your system. Like some of us have work on systems that have been around for a little while, and sometimes they sort of grow up in strange different ways, and you end up with feature sets that don't exactly make perfect sense. If you start creating events and you start saying, this is an order event, or this is a application submission event, or whatever your business may be, I think that's a great way to start making sense of things. And then you can start pulling, because you may have had a function that does 9 different things because that's the way the system was built. Once you have that event, you can start taking some of those things out of that big function and have them instead triggered by the event.
Awesome. But it also sounds like we're touching on our next freeCodeCamp course if we make a domain-driven one.
All right, let's do it.
And I think that about wraps it up. So again, we've linked it throughout the course, but there's a companion blog post at martz.code/e/deep. There's also a lot of really great resources at serverlessland.com, including different serverless patterns that you can use with event-driven architecture and other serverless concepts. Event-driven architecture isn't specific to serverless, but it certainly helps. There's an awesome talk from Eric Johnson from reInvent, and this short code links to that, martz.code/e/ej. And David Boyne does a lot of blog posts about event-driven architecture. He has some really awesome stuff about like different patterns with it and different tool sets. He's made things like the event catalog to help with documentation, and the event canon that can help you, test your own event structures and everything like that. So he also has a reInvent talk about his journey to event-driven architecture, and I have a short link to that at martz.code/e/db. And then my own blog is at matt.martz.codes, and Matt Morgan's links to his talks and all his blog posts and everything is at mattmorgan.cloud.
So thanks to freeCodeCamp for hosting this video, and thanks to you, Matt Martz, for inviting me to join you, and especially thanks for doing all the editing, because I would be bad at that and it would take me a really long time. So I'm glad somebody else is doing that. It's been fun. Anyone who enjoyed this and wants to continue your learning, find me on LinkedIn, find my website. Happy to engage with you and help continue your learning.
Yeah,
Enjoy.
Likewise. Everything Matt said. I'm on socials. I'm martzcodes on pretty much most of them, including LinkedIn. So feel free to reach out to me there. I think we'll try to monitor the comments once the video's out. And definitely check out the companion blog post that we'll be posting alongside this. That will also have the code references and everything too. So yeah, thanks, Matt. Thanks, freeCodeCamp. Hope everyone learned a bit about event-driven architecture. Bye.
Bye. and learned so much about event bridge driven architecture. That was stupid. I said event bridge driven architecture.
You should see my blooper reel. For enhanced security and context specificity. Eric Johnson is a renowned principal developer at Eric Johnson is a renowned principal developer at Git. Wow, I can't say that. Eric Johnson is a renowned blooper reel. Eric Johnson is a renowned... Look at the camera. Eric Johnson is a renowned... All right. It's just... The producer directly manages where and how events are routed, allowing for specific event handling. Let's see if I can edit that. A significant... okay.
Here's Postman. I'm going to make a post to my API gateway to create a new payment. And, oh, sorry. Cut that.
EventBridge offers... Not sure what that's supposed to say.